Okay, we'll take a look at a couple of applications of linear algebra and systems of equations, and then using the Gaussian method to reduce our augmented matrix to reduce Row-Echelon form. In section 1.4 on network flow, there are several problems involving um, material objects flowing into or out of a node. Okay, so I think one of the examples we're talking about number of um, cars per hour flowing into an intersection. In this particular case, they're asked, this is supposed to be a network of pipes, and these are corresponding flow rates. They don't give units, so this could be 50 gallons per minute, 50 liters per day. Don't really know, but you'll see in this entire network, we actually have 40 plus 60, 100, let's say it's gallons per minute flowing into the network, and then exiting the network, we have 50 plus 50 or 100 gallons per minute also exiting the network of pipes. We're interested in finding the flow rate in each of the pipes, F1, F2, F3, F4, and F5. So what I'm going to do is at each of the nodes, each of the 4 junctions, I'm going to equate the entering and the leaving flow rates. So looking here at this first node, I've got 40 plus F3 entering. That will be equal to F1 plus F4 leaving. At this node, I have F1 plus F2 entering. That will be equal to 50 leaving. Here I have, let's see, just 60 entering. That's going to be equal to F2 plus F3 plus F5 leaving. And at this bottom node, I've got F4 and F5 entering, and then 50 leaving. So let me switch over to my whiteboard. Okay. So again, this is section 1.4, applications to network flow. Network flow. Okay. And again, this is an example from the end of this section. So refer to your textbook. So again, at that first node, I had F3 and 40 entering, and F1 and F4 leaving. At the top node, I had F1 and F2 entering and 50 leaving. The rightmost node, I had a flow rate entering of 60, we say gallons per minute, and then F2, F3, and F5 were all leaving. F4 and F5 entering. This was at the bottom node, and a flow rate of 50 leaving. I take this approach of setting the entering flow rates equal to the leaving flow rates. I tend to make less errors when I do that. Other approaches is you could let entering flow rates be positive and leaving flow rates be negative, and then set the sum equal to 0. That's a fine approach too. And I think that's, talked about this being applicable to traffic rates or fluid flow rates. This technique in circuit analysis is called nodal analysis, where we sum the entering and leaving currents at each node. There typically, I take the leaving currents to be positive and the entering currents into a node to be negative, and set the sum equal to 0. But and this is just an alternate approach where I'm setting the entering flows equal to the leaving flows. Now I want to put this in standard form. Okay, so I'll have I want to put all my variables on one side. So I subtract F3 here, F1 minus F3 plus F4. subtract F3 from both sides, and then now I've got just the 40 left by itself. Second equation here is already in our standard form. F1 plus F2 is equal to 50. And similarly for the third equation, I just have to swap the sides. F2 plus F3 plus F5 is equal to 60. And then 2 F4 plus F5 is equal to 50. Okay, so I'll go through the steps here of, here's my augmented matrix, 1, 0, minus 1, 1, and 0. We've got 4 equations and 5 unknowns. Okay. And then my constant here for this first equation would be 40. From the second equation, I've got 1, 1, 0, 0, 0, 50. From the third equation, I've got 0, 1 F2, 1 F3, 0 F4, 1 F5. That's equal to 60. And then for this last equation, I've got 1, 1, and 50. Okay. To get this in reduced row echelon form, I'm going to actually let this first row I'm going to try and keep the leading one in this first row. That means I want to eliminate leading ones in all rows below that leading one. And so what I can do here is, let me copy down that first row, 1, 0, minus 1, 1, 0, and then 40. And then the step I want to take here is actually just subtract the previous row 2, subtract the previous row 1 from row 2. That will give me a 0 here. 1 minus 0 is 1. 0 minus a negative 1 is 1. 0 minus 1 is a negative 1. 0, 0 is 0. 50 minus 40 is 10. And then I've already got leading zeros here in the bottom 2 rows. 0, 0, 1, 1, 50. Okay. So here's my next leading one. I want to eliminate any ones below that. So 1, 0, minus 1, 1, 0, 40, and then 0, 1, 1, minus 1, 0, 10. So what I want to do here is actually subtract row 2 from row 3 to get a 0 here in this spot. It also gives me a 0 here. 0 minus a negative 1 is 1. 1 minus 0 is 1. And 60 minus 10 is 50. And then copy down the last row. Notice rows 3 and row 4 are identical, so it's a consistent. Appears to be a consistent system so far. It looks like I'm going to have to erase my whiteboard. But here I've got my leading ones. This has zeros everywhere else in this column. I've got zeros, but everywhere except in the leading one position here. Here for this leading one, I've got ones above and below, so I want to try and force those all to zeros by an elementary operation. And I see that if I subtract row 3 from row 1, that'll give me a 0 here. Similarly, if I add row 3 and row 2, I'll get a 0 here. And finally, if I subtract row 3 from row 4, I'll get a 0 in this position. So I'm going to do all 3 of those operations involving adding or subtracting row 3 from the other rows in with one matrix. So subtracting row 3 from row 1, I get 1, 0, minus 1, 0, minus 1, and then I get a minus 10 here. So I get this by subtracting row 3, the previous row 3 from the previous row 1, and then here I'm going to add row 2 and row 3, and I get a 0, 1, 1, 0, 1, 60. I'm keeping row 3, 0, 0, 0, 1, 1, and then that was 50, and then subtracting row 3, the previous row 3 from row 4, I get all zeros, indicating again that it's a consistent equation. So above and below all my leading ones, now I've got zeros, so that means that this is in reduced row echelon form. Okay. My lead variables are F1, F2, and F4. Right? F1, F2, and F4. So my free variables are going to be F3. So I'm going to let equal this unknown parameter S, and then F5 is the other unknown parameter T. So now I can solve for F1. From my first row, I'm going to have F1 minus F3 minus F5 is equal to a negative 10. So if I solve for F1, I'm going to get minus 10 plus F3, which is S, plus F5, which is T. And then for F2, similarly, I'll have 60 minus S minus T. And for F4, the remaining lead variable, I'll have 50 minus T. Okay, so I'm going to write the solution in the same form that we used in the previous video for a solution vector, kind of like that form. So write it as column vector. The elements of the column vector are in order F1, F2, F3, F4, and F5. Okay. And then that's equal to a particular solution, which consists of just my constant terms, minus 10 for F1, 60 for F2. F3 has no constant term or constant term of 0. F4, the constant term is 50, and for F5, it's also a free variable, so the constant term is 0 plus S. And then for F1, it involves 1S. F2 is minus 1S. F3 is equal to S. F4 has no S term, and then F5 is my other free variable, so it doesn't have an S term, plus T. And F1 has 1T, F2 has minus 1T, F3 is my S free parameter, F4 has minus 1, and then F5 is equal to T. Okay, so this is the general solution to this problem. So there isn't a unique solution to this problem. An infinite possible number of flow rates are possible. Let me see if I can pull back up the problem here. We actually had 40 coming in and 40 and 60 entering. So we could think about this whole network as a giant node with 40 and 60 entering, and then 50 leaving above and below. And I can't uniquely solve for what's going on inside this node without additional information. Certainly one solution would be with S and T equal to 0, minus 10, 60, 0, 50, and 0, but other solutions are possible. And without additional information, restricting the flow and one of the pipes to have a particular value, then that would give me, actually with the 2 parameters, I'd have to know the flow in 2 pipes to come up with the unique solution. Okay, so I'll give you a problem involving network flow in today's homework. In the next short video, we'll do an example involving balancing chemical reactions.